All right, now the last combination is having an auxiliary equation with repeated imaginary roots. And then I want to combine all the complications that we've learned so far into one example using all of them. Now if a plus bi and a minus bi, which always appear together if they appear at all, appear k times each as roots of the auxiliary equation, then we do maybe what you would expect by now. We'd use the a plus bi, a minus bi solutions, and we multiply each one by x and by x squared, etc., as many times as we need to. Then e to the ax sine bx, x e to the ax sine bx, up to x to the k minus 1 e to the ax sine bx, and then we do the same thing for cosine. E to the ax cosine bx, x e to the ax cosine bx, up to x to the k minus 1 e to the ax cosine bx are linearly independent solutions. To the homogeneous differential equation. So for example, let's say we have fourth derivative of y plus 2 second derivative of y plus y equals 0. So the auxiliary equation is r to the fourth plus 2r squared plus 1 equals 0. Now this factors as r squared plus 1 squared. So that's equal to 0. Now r squared plus 1 factors as r plus I times r minus I, because we have r squared minus ir plus ir cancel, minus I squared minus negative 1 is plus 1. So that's the factorization of this. So if we see r squared plus 1 twice, then this is r plus I squared times r minus I squared. So I is a root twice and minus I is a root twice. So the solutions are now I equals 0 plus 1i, and negative I equals 0 minus 1i. Solutions are e to the 0x sine of 1x, e to the 0x cosine of 1x, and then for the repetition we need to throw in an x, x e to the 0x sine x, x e to the 0x cosine of x. All right, now e to the 0th is 1, so this is just, so the basis is sine x cosine x, 1 times cosine x, and then x sine x and x cosine x. So all solutions are multiple of sine x plus multiple of cosine x plus multiple of x sine x plus multiple of x cosine x. Alright, now let's do one example. I won't write out the differential equation because the example I want to do is so big that it's going to be cumbersome. But let's say we've got a big differential equation and I factored it. So the all complications example is, let's suppose that the roots of the auxiliary equation are one half, 1/3, 1/3, 1/3. Let's say 1/3 4 times. 7 plus 2i, 7 minus 2i, and then -1 plus 4i, -1 minus 4i, and again -1 plus 4i, -1 minus 4i. Then a basis for the solution space is, so we can get away with e to the x over 2 just once, then e to the x over 3. Then since we've got that 3 more times, we need to multiply by x, x squared, and x cubed. So x e to the x over 3, x squared e to the x over 3, and x cubed e to the x over 3. Then the pair 7 plus and minus 2i comes up once. So we have e to the 7x sine 2x, e to the 7x cosine 2x. Remember, there's no I in here. We just take the coefficient of the I. And then we have e to the negative x sine of 4x, e to the negative x cosine of 4x, and then since these roots are repeated, are repetitions of those, then we have to multiply by x. So x e to the negative x sine 4x, and x e to the negative x cosine of 4x. Right. I hope we'll never have to do a problem that big, but if we do, we know what to do with that repetition of the roots. The end.